Yeah, hi there, and welcome to the session here on thermodynamics, water and cooling systems, and refrigeration. The units which are covered by this presentation are 2.6, 2.7, 2.8, and 2.9. Again, if you've been watching the attempted online session, the second online session, apologies many times over. I think I figured out what went wrong. There was some problem here with the computer, and I probably have to have two computers just in case one goes down, especially if it's a live session. Anyway, we're working on it, just beginnings. So hopefully next time it'll be better, and I'm going to make sure I've got some fallback as well, some fallback system. Okay, so let's carry on with the unit. This is what you will know at the end of the lesson. It's various methods to cool water. That's what we're going to look at. There are some really interesting methods as well. Some, go right back into antiquity, and then obviously some of the same concepts. We still use them today in modern refrigeration, but obviously more complex, and we use different chemicals and different media to achieve cooling. But we're going to look at, right from the good old days of the Egyptians to what was happening or what is still happening today. We're going to look at some issues related to water-based systems, and then we're going to look at the refrigerator principles and issues related to refrigerants. So just to anticipate a little bit, one of the main issues is that some refrigerants, especially in the early days, were poisonous or toxic, and some are explosive, so they burn quite easily. And there wasn't really a refrigerant around for quite some time which was neither toxic or explosive. So again, that's one of the issues we were dealing with, and then later we got the CFCs, and everything was better. But then we found out that they are quite dangerous for the environment. We got the hole in the ozone layer, and different coolants had to be developed. Different chemicals for cooling had to be developed, and so anyway, we're going to go through this during this presentation. It should be, I think, reasonably interesting. I hope so. Okay, when and where is it necessary to cool things down using water? That's a big question. We've got a car engine, very important. So if you've got a car engine and you get the warning light coming up, you don't have much time. So it's just going to be a few moments, maybe a few minutes or so, and your engine is gonna cease. It's gonna stop working. So cooling is very important, and we use water as a coolant to cool it. And in a car engine, it's a little bit special as well. We don't want it too cold, but we don't want it too hot either. We've got the thing that water has got a boiling point at 100 degrees. If we pressurize water, or if we put a water in a pressure system, the temperature can go a lot higher, and not a lot, a little bit higher, to reach boiling point, and so we can keep an engine at a comfortable, close to 100 degrees without any problems, in a pressurized system, in a pressurized cooling system. There are a lot of machines where water is used as a coolant, so it's not just car engines, but other machines as well. We use air conditioning, and there are two types of air conditioning. One is based on refrigerants, pretty much the same principle as a refrigerator, and then the other one is based on evaporation. And again, for evaporation we use water as a coolant. We've got power plants, we've got those big cooling towers. Again, they use water to cool down the steam that's generated for the turbines in the condensers. And then we've got, the blacksmith's workshop. If you were to go into medieval days, you would find that every blacksmith has got like a big water barrel stood somewhere, and as he was sort of doing the hooves or the swords or whatever he was creating, they use water to cool down hot steel, very quickly, and as far as I understand, it helped the process of hardening. So again, water was used as a coolant. We've got water-cooled computers, which is quite interesting. So not just air-cooled computers, but water-cooled. And the whole idea is we can use computers at a lot higher speed, and especially gamers, they are sort of into that sort of thing, where they need a lot of processing power. And they can use computers at, clocking them a lot higher and using them for that purpose. What else have we got? We've got maritime engineering. Yeah. So if you've got a boat, obviously it's in the water, so lots of water around, and very often seawater is used for cooling. So we use it for cooling engines and other bits which need cooling within a boat. So we just or one method is to just pump seawater through parts of the engine to keep it cool and to cool it down. And then we've got obviously biological matter such as humans on a hot day. What I'm talking about is sweat, just the principle of cooling. So if you're in a dry climate and it's very hot, your glands will produce sweat and water droplets, and this will cool down the body. So it's for trying to make sure that your body is kept at 36 centigrade and doesn't go beyond that. What are potential problems using water as a coolant? Quite a few actually. Again, electrics. A lot of electrical components are cooled using air or oil. Yeah. So we've got like oil-based radiators. So for example, transformers, they fill them up with oil. And the problem is that electrics and water doesn't mix very well. So if you get a leak somewhere, potentially it's conductive, and you may get short circuits across your electrical circuit. So water is rarely used anywhere with electrics, but there are some exceptions, and we're going to look at one of them in a minute when we look at water-cooled computers. Okay, when we look at mechanics and water, mechanical systems, we've got, even though it makes perfect sense, to use water, it's plenty of it around. One problem is scaling. Yeah, so you could have, if you've got lime or something dissolved in water, it could leave deposits on the cooling system, inside the cooling system. And then the next one is corrosion. Yeah, this is a big problem in mechanical systems. And it's quite interesting when you look, going back to the car engine and the cooling system inside a car engine. Even if you live in a hot climate and you don't really need any antifreeze, it's recommended that you put some antifreeze in your water for your car engine. And the reason is that that the antifreeze will help reduce the amount of corrosion that takes place, for example, in the radiator or in other potentially corrosive parts of the engine. Then the other question is, why don't we just use all antifreeze? Yeah, that might be a good idea. Just stick like lots of antifreeze in and don't use water at all. Especially in colder climates, you don't have to worry about anything. And then we've got another problem. We've got rubber hoses and things like that in our car engine. And if we move away from water and we use like 100% antifreeze or something, then the problem is that that the chemicals will attack the rubber hoses in your car engine, and you've got another problem as well. So what's recommended is like to go for the appropriate mix, which depending on the manufacturer could be a quarter of antifreeze and 3/4 of water, or half and half, depending on the manufacturer, and obviously depending on where you are and what you would need. Then we've got biological and water. So again, when you've got anything biological, which is cooled down with water, so it could be food, it could be other areas, there's a problem of contamination. And the problem is that water is potentially a breeding environment for bacteria. And one example might be algae. Algae sort of develops in water as soon as it is exposed, pretty much as soon as it is exposed to sunlight. And again, it's potentially a little bit of a problem. Okay, let's move on. Why use water? Okay, first of all, it's cheap. There's tons of it around. It's plentiful. It's non-toxic, so it's not poisonous normally. It's easily accessible, so you can get it pretty much anywhere. There's low risk of contamination even though we just said there is a risk, but it's not high. It's can be an open system. Yeah? And so, for example, for evaporative cooling, if you are near the seaside or something, and there's plenty of water around, you could just have a very open system to where you're not bothered about losing anything, so you don't have to have a closed system. Water is kind to rubber, as I mentioned before, so if you've got rubber hoses, they tend to last a lot longer with water than using other chemicals. And there's also some interesting bit about water, and that the anomaly of water, which is where it has the highest density at 4 degrees centigrade. So yeah, that's again, it's an advantage. So it'll settle down. You know, it'll always go down. Cold water is going to go down. Hot water is going to rise. And the beauty about that is that you can use it for cooling. You know, for natural convection. So you don't have to have forced convection in any sense whatsoever, but you just have like a pipe system, and you know that the coldest water is always going to be at the lowest point. Okay, right, let's go further. We've got transformers, and you can see a massive transformer here. And we've got, let me see, I don't know whether you can probably not see the cursor in the video. Anyway, we've got a massive transformer here. And you can see those grills on either side of the transformer, and they are cooling grills. So that's meant for cooling. So you've got some fins, the air blow through those fins cools the oil down. And over here we've got an expansion tank as well. So if the oil heats up, it expands a little bit, so it moves in there. Now the big question is, why don't transformers use water for cooling? It would make perfect sense. It's cheap, it's plentiful. It's very effective for cooling, but we use oil instead. Again, the answer might be quite obvious. When you've got a transformer, the voltages can be quite high, so you can be talking about 32,000 volts, possibly a lot higher. And water is conductive, oil isn't. Oil is an insulator. So if anything goes wrong with the transformer windings, so maybe you could get away to for some time using water as a coolant. But the problem is, if anything goes wrong in the transformer, you'll generate a short circuit through the water straight away, so it's not used. I'm not sure whether you've seen the health and safety video. If not, remind me, and next time in class we can check it out. Normally I tend to show a video of transformers blowing up, you know, transformer going wrong, and it might be in the 308, and I'm not sure whether I've done it or not. I will eventually if you haven't seen it. But one thing you can see is, and this is sort of the downside, because oil, once mixed with other stuff, can burn. And so when transformers go, because something has gone dramatically wrong, they actually burn up, and they go up in a big flash with the oil around, and it looks quite scary. Obviously, with water you wouldn't have the problem, but they would go a lot earlier. So anyway, that's the reason. Electrics and water generally don't mix. We need oil, you know, especially if there's potentially a small fault in the insulator around the transformer windings. The oil doesn't mind; it copes without a problem. It adds to the insulating properties, and that's the reason why we use oil in transformers and we can't use water. Automotive cooling. We looked at this earlier, and you can see the diagram here. I'm going to try to move my cursor around. So you've got the radiator here, yeah, and you've got the cold water pipe at the bottom, the hot water pipe at the top. It all mixes up, goes through the engine block, so it tries to cool down the engine, yeah. And then we've got the matrix right at the back as well. So that's pretty much in the near the driver's feet. We've got some air. We blow some air. This is a fan. We blow some air through, and then the hot air is then moved into the car's interior to keep you nice and comfy. So that's the concept of the radiator, and everything that's in there is just water and a little bit of antifreeze. Again, as I mentioned before, these pipes are made of rubber, so you've got a lot of rubber in your automotive cooling system, and the rubber would go, if you used antifreeze only, it would go quite fast, so that it would not last its lifespan. And on the other side, if it's only water, the radiator starts corroding pretty fast, so you use the antifreeze as a corrosion inhibitor. We've got a thermostat as well. The thermostat controls the temperature. Again, it's a very clever cooling system. We need to keep the engine at a certain temperature, optimum temperature, and that's what we use the cooling for, or the thermostat, to try and just keep it at the right temperature. Okay, next one. Just another picture of a car cooling system. The cooling takes place through air, which is forced through the radiator. The water in turn is cooled down, and the water then cools the engine block. Again, we've got like another blown up diagram here. And you can see this here as well. I'm not sure whether you can see the cursor. So that's the top left diagram. It shows the air, how it is pressed through the radiator. And if the car stops and it gets too high and it's not enough cooling taking place, we've got a fan here, and then the fan would kick in and blow some air through the radiator to enhance the cooling. Couple of questions I've got here, and let me just ask them to you. What would happen if the water pump failed? Okay, let me just wait for a moment and then let you think about this. What would happen if the water pump failed? You can see this here. We've got a water pump. The water pump is used for convection, so it's forcing water through the cooling system. What would happen if it failed? It just doesn't turn around anymore. Okay, I'm going to wait. 30 seconds. Okay, so it's almost 30 seconds. No, that's 30. Another 10 seconds. Okay, so if the water pump failed, there would still be some movement of the water through the circuit, and that movement would take place just by the fact that hot water rises and cold water falls down. So you would find that that there would be a very slow movement of water through the circuit, and cooling would actually take place. And maybe the other way around, I'm not sure. Would be interesting to work it out, but eventually it would take place, and just through natural convection. Yeah, so but it would be very slow, probably not enough to keep the engine running in good health, and I wouldn't try and test it out. So if your water pump ever goes down, get yourself to a garage and have it changed, or change it yourself. It's an important piece of kit in your car, so it's important to push the water through the radiators and through everything else, so you can't rely just on natural convection. If you look at heating systems as well, where we've got not water as a coolant, but the opposite, as a heating medium. When you look at really old systems, you can actually see pipes, and the house was probably built in the 40s or 50s or something. You can see really fat pipes. These pipes then move through the house, and and you would have a boiler somewhere in the cellar, low down. So the boiler heats up the hot water. The hot water in turn would rise up, and work its way through the pipes, and then sort of the cold water would fall down again on the other side and be heated up again. And this was sort of old heating systems. They wouldn't have a pump or anything. Literally, they only had a boiler, and they were relying on the water finding its own way and the hot water working its way through the system. It did work, but the problem was that, and still is, if there's still a system around, I've seen once one in an industrial building. It used to be a cloth maker, so a little factory, and I've seen the heating system in there, and the problem there was that it takes ages to heat the place. Yeah. For the water to work its way around and to start heating the place, it would take a very, very long time. And that's a problem. So if you're just installing a pump, would speed up the process. Yeah. But it does work, and it does work eventually. Next one is, what would happen if there's a thermostat failure? And again, you've got a thermostat here. I don't know whether you can see the mouse. It's there. It's in the circuit between the hot and the cold water pipes. What would happen if your thermostat fails? Okay, the answer is the temperature of the water. It's for a car thermostat. It's how shall I describe it? It looks a little bit like a valve, which has got some sort of bimetallic coil, and the coil sort of expands and presses against a flange, and if it does it, there's very little water which can go through the circuit, and if it gets too hot, then it opens up and it allows a lot of water to flow through. So that's pretty much the way it works. It's just a little mechanical device. The general fault tends to be that something goes wrong and the bimetallic spring doesn't work anymore. It's just permanently closed, and in that instance the temperature would just rise really, really high, and there's not much you can do about it. You would get the little warning light coming up, and you should really make sure you stop your car very quickly. And one trick to find out whether it's it's a thermostat fault, what you do is you check the temperature before, you can just feel it with your hands, before and after the thermostat, to figure out where the fault is. Yeah. And if the again, be careful. Yeah. Ideally, what you should do is you should get a temperature sensor, remote temperature sensor, and you could check the surface area on the pipes. That would do the trick as well. So you don't need to use your hands. If it's really, really hot, you can scald yourself. So make sure the engine is cooled down sufficiently before you attempt this check, and make sure the engine is turned off as well. It's very, very important. But a quick check will actually tell before and after the thermostat of whether it's working or not. If it's working, the temperatures should be very equal. Otherwise, one side is really cold, the other side is really hot. So it's going to be quite a difference, and then that's an indicator that your thermostat has gone down. It's not a great job. You can change it within a very short time, but normally you don't have like a thermostat at hand, and I think in my driving career it's only happened once. Twice actually. No, it's happened twice. I had it on 2 cars. I'm just sort of trying to memorize, but on 2 cars it's happened where I had a digi thermostat. Okay, so the thermostat, once it's broken, it's normally closed. That's my experience. Temperature of the engine goes sky high, and you really need to change it. If it's wide open, and I've experienced this once. I once had a problem on my car. The thermostat was permanently locked. I couldn't do anything, didn't have any tools. Called out the recovery service, or the AA guy came, and all he could do was just take the thermostat out and put the thermostat housing together. So I took the thing out, put it together, and the car worked again. It wasn't overheating, but the temperature was really, really low. Yeah. So when I turned on the heater, it was just like lukewarm air which was coming out of it, but it wasn't hot air. So the car worked, wasn't quite as economical, but that would be the other extreme. The thermostat opens up all the time, and then you don't get the temperature you're actually aiming for, which is sort of about close to 100 degrees for your car. Okay, let's move on. Go to the next slide. Okay, we've got a couple of cooling plants, yeah? And the first thing we're going to talk about is evaporative cooling. So the principle is that your Let me just see if I got some other slides. Yeah, you can see this here. The principle is that you've got evaporation taking place, and whenever water evaporates, a lot of energy is released, and it's actually got a cooling effect. I mean, one way you would have experienced this if you go on a really hot summer's day, you jump in the water, and then you get out of the water, and you should be fairly warm straight away, but as a matter of fact, as the water is evaporating from your skin, from off your skin, you actually feel quite cold. Yeah? A lot colder than what you would expect, it being a hot summer's day. And that's down to evaporation. In this system, and you can see this machine, that's a machine, and it uses evaporative cooling, where water evaporates, and you've got some centrifugal fan to blow the air, and as a result, you get cold water leaving the plant. So it doesn't cool as far as freezing water, but it can cool it quite a few degrees. Yeah. So it's a system which is used. Okay, we've got another flow schematic, a schematic diagram of a closed loop cooling water system with a dry air cooler for a single VIP unit. Yeah. Just to let you peruse this for a little bit. So we've got a dry air cooler. Yeah, so we force air through water, and this is meant to cool it. Okay, and here we've got another one. Again, when we look at water cooling in general, we've got the water-cooled PCs. You can see what they look like. So I'm not sure whether you can see the mouse. I'm looking at the left-hand side now, the cursor. And it's just like a little patch which you put on top of the CPU. You've got some thermal paste to stick it onto the CPU. And you can see you've got some water pipes which go all the way through to this cooling device here. And it's meant to keep the PC cold. And again, it's ideal for high processing applications. Generally, people who have got a PC, and the stuff that gobbles up most of the power tends to be games, computer games. Okay, so we've got that as well. You can see some other examples as well. So here on the right-hand side, top right-hand side, with the blue pipes, that's also a water-cooled PC. So you've got two big cooling pipes here, and then you can see down here as well, just a few more examples. So actually, it's done. I've been told that they have to use distilled water, just in case there's some sort of spillage. Distilled water is normally not conductive. Only as soon as it gets any impurities, it starts becoming more conductive, to the point that it could cause a short circuit. So you use a special type of water in these systems. That's what I've been told. I've never used them or had them. I think they look quite cool, and I was quite tempted to actually try it out and see, looking at these pictures and putting them together for this presentation to see what you can do with water-cooled PCs. Okay, we've got power plant cooling towers. You can see the diagram here. There are quite a few of these towers around here in Yorkshire. The most visible one is probably Ferrybridge, which is just right next door to the A1. And then we've got Goole. And there's another one. Is it Agborough? I'm not sure. Anyway, there are three of them, just east of Ferrybridge. And Ferrybridge has been taken out of operation. I think it's been mothballed, but it's not working at the moment. Now, I remember sort of being near these towers whilst we were working, and it's quite interesting. Around these towers, even if you're sort of 100 yards away from them, there's some sort of microclimate, and that is just it feels really cool and uncomfortable, even on a warm day when you go anywhere near them. The sound when you are next to these towers is like sitting next to a waterfall. It's quite amazing. If you ever have a chance to get anywhere near them, try it out, and you can see it. Now the whole idea, and we can see this here in the bottom right-hand side picture, is to cool down steam, which comes from the plant, from the turbine. So the steam goes back, all the energy is in the steam comes back, and it needs to be go through a condenser, and it needs to be turned back into water. And to do this, we have these cooling towers. And what you find as well is that very often the cooling towers are built near ponds or near a river, so they've got ample access to fresh water. I mean, the amount of water that's used must be phenomenal. The steam that's rising up, by the way, is just steam, water steam. So it's not dangerous, it's not a pollutant as such. But it takes up a lot of water. Okay. Yeah, by the way, the shape of the towers is quite important as well. It generates a draft, an upward draft. And again, it's used for this whole concept of this evaporative effect. And you can see when you look on the bottom left-hand side picture, you can see there's certainly evaporation taking place. So that's not steam from the power plant, but that's actually the evaporation of the water that's been blown over the pipes where the steam is pumped through. Yeah, and then some of the water goes back into the river, and some of the water just evaporates. And the effect of evaporation helps for the condensation of the steam, to turn the steam back into water. Okay, let's move on. So we already talked about evaporative cooling. Just a little reminder of how it works. You think about summer, you think about a hot day, you have to swim in a lake, and you come out of the water, and despite being hot and sunny, you feel really, really cold, because your skin is all wet. And what's happening now is that the sun is sort of evaporating the water on your skin really, really fast, and whilst it's evaporating it cools your body down. And the same thing as well. So if you live in a hot climate, and people are about to suffer a sunstroke or something, or feel a bit squeezy, the best thing to do is to just take some wet towels and put them on people, and the evaporation would actually cool the towels down, and people will actually feel quite cool and comfortable. And it's interesting as well. I mean, this effect from swimming in the sea and then getting out of the sea, and this effect of feeling cold is a lot more pronounced when it's really sunny, as opposed to when it's cloudy and the sun is sort of hidden behind the clouds. And yet the environmental temperature is still the same. I mean, try it out next summer. Last summer was quite amazing. Maybe the next one to come is going to be amazing as well. If you've got a chance, try it out, and you can actually experience this on your own body. Why? Again, the question, whenever evaporation takes place, a lot of energy is released, and in this instance, you've got the cooling effect. Yeah, so cold is released as the water evaporates. Okay, evaporative cooling. This is how it works. So again, when you're in a hot climate and you've got high levels of humidity, I think over here we say, oh, it's muggy or it's sticky. And if there's a lot of humidity around in the air and evaporation, you are wet, and evaporation doesn't take place, there's not much cooling which takes place, and there's not much relief from the heat. And that's the reason why it is sometimes very, very difficult to work in tropical climates, because you can't cool down. You sweat, your body systems don't work properly, so you don't evaporate sweat to cool down your body. You can't use water, to slush it on your body to cool down. So the relief from the heat is very little. In a dry climate where you've got very little humidity, sweat evaporates, and you find more relief from the heat. And so it works fairly well. That's the reason why dry heat is a lot more bearable than humidity, or being in a climate where you've got a very high level of humidity. Body's cooling system. Just to look at this, the blood circulates closer to the skin, so heat is lost. Body sends sweat to the skin surface. Sweat evaporates off the skin, and in this sense it cools down the body. And again, the body temperature should be somewhere between 36 and 37 centigrade. And the body tries to do anything to try and get you there. Okay, move on. Evaporative cooler. Evaporative coolers are ideal for places where there is a lot of heat and a dry environment. Yeah? Again, a desert would be ideal for an evaporative cooler. So you've got lots of heat, you've got lots of sunshine, and it's a very dry environment. So evaporation takes place, and the air is getting cooler. So in a rainforest, it wouldn't work, or not that well. Only obviously when it's not raining and when the humidity of the air around the evaporative cooler goes down. Once you do this, you just have got some airflow. You force the airflow either through forced or natural convection through the cool medium, the dust filter or whatever it may be, and you get nice cool air coming out of it. Yeah. So obviously it doesn't freeze. You don't get little chunks of ice or anything like that, but you get cool air. And you could put your drinks in there and you cool them down. I mean, one thing which we do here, and I'm sure you've come across this, is, for example, the garden party in the summer when it's really, really hot. And you can't really have a fridge outside, so people just get a big drum of some sort or another, fill it up with water, and then they put, the canned drinks, the beer bottles, whatever it is, in the drum full of water. And as the water evaporates, it actually keeps everything nice and cool. So you don't get frozen beer, you don't get like really, really, really cool beer, but the evaporation keeps it a lot cooler than the environment around. So if it's about 30 degrees out there, your beer is certainly going to go down below 20 degrees or something. Again, I haven't tested it. I'm not running around with a temperature gauge all the time to try and figure this out. But it might be interesting as well. It might be something for the summer to try and find out what difference it makes. It certainly you certainly feel the difference. You certainly taste the difference. But anyway, just check it out for the summer. Right, now we are going back to a really old way of climate control, and where we use water as a cooling agent by using evaporative cooling. First of all, running aircon units is very expensive, and evaporative cooling for climate control is an efficient alternative. Efficient because it doesn't, you don't need any energy for it, and the method has been around for thousands of years. And in the olden days, that's what people were doing. So if you lived somewhere in the Mediterranean and it was getting really, really hot, you had like some pool in the cellar with water, filled up with water, and possibly a water supply as well. The Romans were pretty good with that. And you would have some air blown over the water, causing evaporation. And with that, the air would cool down and it would sort of blow through the rest of the house. And inside the house, it would be nice and cool. And outside the house, it would be incredibly hot. It's a big question. What is the snark about evaporative cooling in desert climate? Give you a moment. The obvious problem is it's getting the water. Yeah. So if you live in a desert somewhere, most likely there's not going to be a lot of water around unless you live near an oasis. Or then again, in the Mediterranean, it can get quite hot. It tends to be reasonably dry. But if you live near a river or near the coast of the Mediterranean, then it shouldn't be a problem. Yeah. So you've got water available to use for your cooling. Now this particular picture here you can see is in Las Vegas, Nevada, and they've got a desert living center there, and as far as I understand they are trying to revive these old technologies of having climate control and keeping the building nice and warm during the day, nice and cold during the day and nice and warm during the night. Okay, just a couple of pictures. You can see, I think most of the pictures here on the left-hand side is all done in Nevada. Then on the right-hand side we've got Desert Spring in Spain, and you can see the pool there as well. And very often pools like that, they put them. It's not just for swimming around, but it gives a pleasant climate, around the living areas by cooling down the air a little bit due to evaporation, and it actually does work. And I'm sure you've noticed this when you go to a pool. You can see the houses are built all the way around it, so if it heats up a lot, you get some evaporation taking place, and the air around the pool is going to be nice and pleasant and cool as well, as opposed to walking away from the pool. Then right at the bottom there, bottom right hand side, we've got the windcatchers of Dubai for evaporative cooling, and they're really interesting. I mean, they have been around for thousands of years, and it's an old technology for desert dwellers. And I think we've got a picture somewhere. Let's move further. I'm going to go back, so don't worry. This is the evaporative cooling using a windcatcher, and I'm not sure whether you can see the picture. So you've got the wind which is caught up, and it's just blown. It's just sucking air out. So right, start again. You've got the windcatcher here. The windcatcher sucks air out of the building, and the air is forced through a plane of water. So you've got a water channel, maybe a well or something like that, where you've got some groundwater. So the air sort of moved across the water, goes into the living quarters, and then is moved out of the building. And so you're kind of naturally sucking warm air out of the building, and you're sucking cold air, which is being cooled down with water through the building. So that's how they work. That's how the windcatcher works. And it's an earlier form of evaporative cooling. It was first used in ancient Egypt and Persia. So Persia is Iran today. Thousands of years ago, in the form of wind shafts on the roof. They called the wind, passed it over subterranean water in a carnot. So the carnot is the little water thing down here, and discharged the cooled air into the building. Modern Iranians have widely adopted powered evaporative coolers. Yeah. Again, if they are powered, you can use them all the time. You don't have to wait for the wind. But the beauty is you don't have to pay a huge amount of energy like you would have for air conditioning units. Yeah. So the energy is pretty much free. Okay, let's go back and okay, so we've got like little aircon units here. That's an evaporative cooler. Information has been taken from Wikipedia. You can see the link up there. They're also called swamp coolers, swamp box, desert cooler, or wet air cooler. And it's a device that cools air through the evaporation of water. If you've got a traditional aircon unit, a mobile or portable one, you would have a big pipe at the back of it, and you would have to pull the pipe out somewhere, and blow the warm air outside the area which you want to cool down. With an evaporative cooler, you don't have to do this. Yeah? So you just literally evaporate the water, and you can do this by forcing air over the water. And so the hot air from within the room, the building, wherever you are, which is blown over the water evaporates, and in turn blows cool air out. Obviously, it doesn't work in wet climates, but it's ideally suited for dry climates. It's better for the room environment, because you blow humidified air through the room. Yeah, so the climate gets a little bit better, but also it cools it down quite nicely, and it's very cheap to run. You don't need a lot of electricity to run it. Again, evaporative cooling differs from typical air conditioning systems, and normal air conditioning units, they use vapor compression. Yeah. Okay, next one. Evaporative cooling uses the fact that water will absorb a relatively large amount of heat in order to evaporate. Yeah. So again, that's good as well, because we get rid of our heat and we get some colder air. Right, let's move on. You've got an evaporative cooler here. I'm just going to leave it up for a moment. You always need water, obviously, makes sense. You would have some sort of fan to blow air over the water to allow it to evaporate. Yeah, that's it. So that's evaporative cooling units. I've never really seen them in this country. And to be fair, I haven't seen them in places where I used to work, like in the States or in... the only time I've seen this unit, I'm lying, I just remember, I was working for 3 months in Pakistan a long time ago, and they used, it's quite interesting, they had a, a system which was a washing machine and an evaporative cooler, a 2-in-1. And they were selling them there quite a lot, and I saw them in operation once. And again, the whole idea was, you know, you've just got a drum, you put lots of water in, the thing moves around, and in doing so, sort of promotes the evaporation of the water. But if you put some clothes in it and some washing up powder, same thing, you can just use it as a washing machine. There are like 2 modes for one device to use it the same way. And over there, it made sense. It was just a very cheap way of air conditioning a small room, and it did it work. I mean, when I was there, I don't think it was ever used. I was just sort of intrigued to see at the time how these things work, and you saw them pretty much anywhere you went. If you visited people, they had one of these things in the corner. Just another diagram of an evaporative cooler. And all it is really, you know, on the lowest level, you've got a little bit of a motor, you've got like a fan to blow the air out. The air is sort of blown over some water. And that's it really, that's all it is, that's all there is to it. Okay, we looked at this one. Ancient cooling methods. I think I mentioned this in the sort of introduction. It's a really interesting way of cooling water. And that's, again, is you know, something that's been used for thousands of years, and it might be worthwhile if you ever find yourself in a desert somewhere and you need to conserve your food. There are normally 2 ways of doing this. One of them is to cool it down. If you manage to cool it down to about 5 centigrade, bacteria, which cause the food to perish, they can't multiply, or they don't multiply as good. And you can preserve it for a longer time. The other way was obviously to dry everything, and this was another method of preservation, to dry your food and to then add water later and to eat it. But anyway, this is how this cooling works. You've got 2 pots. You've got an outer and an inner pot, and you fill some sand in between those 2 pots. So then you put the area, or you know, the stuff that's been filled up with sand between the 2 pots, you fill it up with water. So the sand is going to be soaked in water. And then you've got the outer clay pot, the inner clay pot, and you put a wet cloth over the food. And you then start evaporating, you know, heating up the pot, the water evaporates, and it'll naturally, through evaporative cooling, cool down the inside of the inner pot. So all your vegetables, your fruits, whatever you put in there, is going to be cooled down to a nice, you know, low temperature, 5, 6, 7, 10 degrees, which again in a desert climate is really good. You know, looking that you're probably having about 30, 40 degrees in the sun. With that thing, you can actually cool it down and preserve your food a lot longer. So the heat transfer takes place as the water evaporates. Okay. Next one. We're now going to look at refrigeration systems, and again the need for refrigeration. First one is food preservation to cover the winter periods, also to have in the summer periods when it's really hot, to make sure your food lasts longer than a day, you know, once you harvest it. Shipping is a biggie today, especially. You've got like a lot of refrigerated systems on ships and elsewhere. So for example, when fish is caught, they pretty much freeze it straight away. So they need to be able to cool it down as best as possible. Military as well, for various purposes, you know, food preservation and so on. And again, it's interesting. So we're going to look at early attempts Early attempts are from the 1800s, when they, I think it was 1850 something, when they first managed to artificially produce ice. Before you had ice cellars, evaporation cooling was known. People were using it in the 1800s. We also had ice houses, you know, for fish and things like that to keep them cool over longer periods of times. And we had also something which is really bizarre, it's sort of this winter ice harvesting. And this went on up to the late 1800s. I think I mentioned before, in Canada, in the 1800s, there was a lot of ice and snow, and so they had ships which had very good insulated chambers. They harvested the ice in Canada, and they would put it in these chambers, and then they would sail all the way down the American coast, all the way to the Caribbean, and they were selling ice. So they're big blocks of ice, and they would sell them off, you know, for people to put in their cellars, on well-insulated cupboards to then cool down their food. So that was the way it was done sort of in the 1800s. So the method was known, but because we couldn't produce the ice artificially in those days, so we waited for winter, then got hold of the ice and snow, compacted it, and used it all the way up to summer. So that was the kind of stuff which was taking place. Really bizarre from today's point of view. And you think, you know, how did they survive? What did they do? But it did work. They did it. Refrigeration research. It started in the 1700s, and in 1755, William Cullen, he made some attempts, and he actually managed to burn up some ether, or boil some ether, and he could extract heat from the environment. And he even had a first for small fridge on artificial ice construction. I'm not sure whether they actually managed to get ice. He just managed to cool everything down, but it was some sort of fridge. Then we had Benjamin Franklin, who was the US founding father, and he was a bit of an inventor and did all sorts of stuff, and a guy, John Hutley, and they worked on a project together which was organized by Cambridge University, and that was 1758, let's get it right. And they were producing, using ether and alcohol, and they were managing to get water frozen below 0 centigrade, so that is below the freezing point. So they were, around about that time, was the first experiment to get like tiny cubes of ice or something, but there was no commercial interest at the time. And it took about 100 years for somebody to come up with the first vapor compression refrigerator, using a closed circuit system. So before they were just, you know, boiling some ether or something, and they could generate cold environment. And then they had a closed system, a closed circuit system, and that was sort of 1830s. But there was little commercial success at the time. So it took another 50 years for them to become commercially viable. By the 1890s, refrigeration was widely used in the food distribution industry. So suddenly the industry realized, hey, we're onto something here. If we start freezing our food, we can, you know, ship it a lot further, we can move it a lot further away, and we can have a far bigger market to sell the food we have. Home refrigeration, so having a refrigerator in the home, didn't happen until the 1920s to 1930s. So that was sort of around about that time is when people started buying small refrigerators and stuck them in their home. So in other words, a refrigerator is, the domestic refrigerator is barely 100 years old. So interesting. I thought a little bit of history. Okay, I've got a lot of text here. I'm not going to go through all the text. Just going to talk you through a little bit. You're on YouTube, so you can stop the slide and just read through it and work it all through. And just explain the diagram. So the top diagram is pretty much a refrigerator. We've got an evaporator. The evaporator is pretty much the stuff which is inside your fridge. So you've got like a little bit of a grid inside your fridge. It looks a bit like a radiator or a couple of pipes or something. Normally they're always iced up. You know, you get condensation inside your fridge. It ices up. And then on the other side, you've got a condenser. The condenser boils the the refrigerant, or heats up the refrigerant, and the condenser is the place where the vapor is turned back into a liquid, and then we've got a little bit of a valve, and the valve will allow the liquid to go through. So we've got a liquid vapor, and this liquid vapor in the evaporator will be cold, and if you've got some forced air behind it, it'll blow forced air or cold air on your products, on your whatever you have, on your food or whatever. The compressor in turn compresses the vapor, and again it moves it into the condenser. So you've got this circuit going on, and so on one side it's very cold, the other side is pretty warm. So when you've got a refrigerator, always bear this in mind, you need a lot of ventilation behind the refrigerator. The temptation is always there to put some stuff on top of your refrigerator and to block off the airflow from behind the refrigerator. You need to have quite a bit of a gap behind your refrigerator and allow air to flow freely so that the condenser can work at its best. Okay, below you've got a diagram where we've got the whole process of from a liquid going into a vapor, from a vapor liquid back into a liquid, and we've got this circle where we've got the evaporator and the condenser, to one releasing hot air, the other one being very cold. That's the basic concept of evaporation. Now this works pretty much with to some extent with most liquids, but some liquids are really well suited for this, and they will actually allow you to generate temperatures below the freezing point, below 0 centigrade, and which are propane. I've got a list somewhere, let's have a look whether we can find the list. Let's have a look, do we find the list? No, I think it's in the text somewhere further up. Okay, so one of them is propane. We've got ethanol, we've got alcohol, which works as well. Again, the problem is with those refrigerants that they're either toxic. Ammonia is another one. They're either toxic or explosive, and none of them is good, especially not in the food industry. And so then we came up with the CFCs. Right, let's have a look. This is the back of a refrigerator, and whatever you find in industry is pretty much the same concept. It's just the scales are obviously different. You've got bigger compressors. Okay, so let's have a look at this little fridge down here at the bottom, the animated fridge. We've got a compressor which pumps the liquid through the or the vapor through the system. We've got some, most likely the valve is in there as well. Then we've got the condenser, which is at the back of the fridge. And then we've got the evaporator, which is on the inside of the fridge. You can see again the inside of the fridge just looks like a radiator really on a car, but that's the evaporator. And then we can see at the back of the fridge we've got these pipes which are meant to turn the vapor back into a liquid, and that's the condenser. And then we've got again at the bottom the compressor. It just goes around. It really is a very simple system, and we're going to look at maintenance as well. It's not that much that can go wrong with them, and if something goes wrong you can pretty much recognize it straight away. Just a few tests and you can fix it. Okay, refrigerants is a substance or mixture, usually a fluid, used in a heat pump and refrigeration cycle. It undergoes phase transitions from a liquid to a gas and back again. And fluorocarbons, especially chlorofluorocarbons, so that's CFCs, became commonplace in the 20th century, but they are being phased out due to their ozone depletion effects. Other common refrigerants used in various applications are ammonia, sulfur dioxide, hydrocarbons such as propane. And I'm not sure whether it comes up in this presentation, but just remember, they're now looking into carbon dioxide as being used as a refrigerant. And that would be great, because carbon dioxide, even though you hear a lot about climate change and all this stuff, but in the grand scheme of things, the carbon dioxide you would need for a refrigerator wouldn't be that much, would just be a tiny amount. A lot less than what you use in your car. Anyway, it's not toxic, which is a great advantage. It's not explosive, which is a great advantage. And it's cheap. It's all over the place. And it doesn't cause a hole in the ozone layer. So carbon dioxide might be the future. And who knows? There's some research going on at the moment. I'm not sure whether commercially there are fridges available with carbon dioxide or CO2 as a refrigerant. Would be interesting to check it out. Maybe a little bit of homework for you guys to do, to see. Okay, so we've got then the other ones, common refrigerants used in applications are ammonia, sulfur dioxide, hydrocarbons such as propane. So propane, that's the stuff you get in your camping bottle. That can be used as a refrigerant as well. So camping gas and things like that. I think they use a mixture of butane and propane. It's sort of half and half. But anyway, that's where you find this stuff, and you can use it as a refrigerant as well. I drive a car with LPG, so I've got liquid petrol, LPG, gasoline, I think it stands for. But anyway, liquid petrol gas. And one of the things is, as well as it's stored as a liquid, so I get it as a liquid, pump it in my tank. And then I've got the vaporizer. Yeah, it turns it into a vapor, from a liquid to a vapor. And here's the thing: if there's a problem with my radiator circuit, there's not enough water in there, it actually starts freezing up. It's quite interesting to see. It's happened to me once where I lost some water, and suddenly the gas circuit didn't work, but I had plenty of gas in the tank. And what I noticed is that it was just vaporizing, and there was a big chunk of ice building up around the vaporizer. Yeah, so it's just one example, or a real example, how this can be used as a refrigerant. Yeah, and that's just a hydrocarbon. I'm not sure what LPG contains. I think it's propane and some other stuff in there, but it's pretty much the same stuff. The ideal refrigerant, the desired thermodynamic properties is the boiling point somewhat below the target temperature. So whatever temperature you're looking for, whether it's 5 degrees, 20 degrees, 10 degrees, or minus temperature, maybe minus 5 degrees or 10 degrees. It should a high heat of vaporization, should have a moderate density in liquid form, a relatively high density in gaseous form. A high critical temperature, should be non-toxic, non-explosive, and should be environmentally safe. Yeah, that's the ideal refrigerant. There used to be a big cry out with the CFCs because they pretty much fit into this criteria, and they were ideal for fridges and stuff like that, but they caused a problem with the hole in the ozone layer, and so it was decided that they had to be phased out. And people were shouting out and crying out, "What now? What can be used? What refrigerant can be used instead?" And I think a lot of attempts have been made to build fridges not using CFCs. And I think today, if you buy a fridge today, there won't be any CFCs in there, but they use an alternative refrigerant. Yeah, it's in my presentation. I thought I put it in, but I wasn't sure. The promising alternatives now is CO2. It's a carbon dioxide, it's non-flammable, non-ozone depleting, and it's non-toxic either. Yeah. So it's not to be confused with carbon monoxide. Carbon monoxide is highly toxic. It's if you breathe this in, it's going to kill you in no time. CO2 is not. Yeah. There's CO2, plenty of CO2, not plenty, but CO2 in our atmosphere. So you're breathing it in every day. CO2 is the bubbly stuff in your soda. Yeah, it's carbon dioxide. So the little bubbles on your Coke, inside your Coke, or something. That's CO2, and they want to use this stuff as a refrigerant. It can be used as a working fluid in climate control systems for cars, residential air conditionings, hot water pumps, commercial refrigeration, and vending machines. So that's what they're looking at for CO2. And the beauty as well is you're drinking it in your soda, in your pop. Yeah, you're drinking CO2 all the time. It doesn't do anything to you. It makes you belch maybe, and that's pretty much the maximum. But it gives you a sensation of a fresh drink, and so on. But so it's not dangerous at all. So it's ideally suited for the food industry, because should it get mixed up with food, won't do anything if you've got a leak on a refrigeration system somewhere. Okay, maintenance aspects. Yeah, need to look at that one as well. So what happens when your refrigeration system goes wrong? And we're at the end of the presentation as well. You'll be pleased to hear. So a couple of things can happen. So we can have a loss of refrigerant. So we can have a leak. So if that refrigerant goes down, you check for leaky pipes. And sometimes it can just be a microscopic leak. But over time, the refrigerant will just, especially once it gets vaporized. So the liquid might not complain about the leak. It might not leak out. But once it's vaporized, and it's just a gas, the gas might just leak out of it. I've seen this once in an air conditioning system. And it had to be refilled every couple of months. And I noticed, it was quite interesting, when you went into the room, where the leak was, if the room had been stood still, had not been used for a long time, there was some sort of mist in the room. And that was just the refrigerant of the air conditioning system which leaked out. It took them ages to find it. We got the company out who had installed the system, but they went out about 3-4 times, and all they did was just initially reload the air conditioning system and say, oh, we don't know why it's going out, but it was obvious there was a leak. Yeah, they were just it was so small that they couldn't locate it or couldn't find it anymore. It took them ages to find it. Loss of compressor function, so your compressor might go down. And there might be several reasons for it. One might be just electrical, that there's a fault in the supply. So first of all, I would check the wiring for the compressor, make sure that power is fed to the compressor. You can normally hear it as well on a fridge, when the thing runs, whether the compressor kicks in or not. So it's one way to find out what's going wrong. It might be an expansion valve. The expansion valve, which again is most likely inside the compressor somewhere, that it might be faulty, and then the whole circuit of vaporization and condensation doesn't work too well. Sometimes you get the effect that actually the fridge on the inside heats up, and the outside cools down, something like that. If that happens, it's an indication that there's either something wrong with the compressor or the expansion valve. Yeah, that one has just gone dicky or something happened to it. So it can happen. A broken thermostat. So you've got a thermostat inside a fridge, and if that one breaks, it might either cool down to crazy levels or it might not cool down at all. Yeah, so again, the first one is just change. Most of them are very simple thermostats. It might be just a bimetallic strip making a contact. I would mess about with the settings to start off with to see when it kicks in, and then check this with the temperature. Or just see what's going on. Maybe check the connections of the thermostat, the wiring, that the wiring is okay, that it's not corroded or dropped off or some damage to it. And then also do a resistance test. Sometimes, depending on how the system works, whether the thermostat uses a high voltage or a low voltage, if there's some dirt on the thermostat and it's a low voltage, it's will build up some resistance, and it might not allow the a signal for the compressor to kick in. If it's a high voltage, which goes through the thermostat for the compressor to kick in, you might get something which is called carbonization. So they carbonize. So you get the contacts, there's some sparks and arcs, and over time they build up quite a bit of resistance, and it might just be too much for anything to go through to allow the compressor to kick in. So again, the easiest option there is change the thermostat, put a new thermostat in. To jerry-rig, something like that, if you cannot get access to the thermostat, inside the thermostat housing, if it's a very urgent job. It's a workaround, a temporary workaround, because it's going to happen very quickly again, is to possibly look at the contacts and to clean up the contacts of the thermostat. Yeah, it's most likely some bimetallic contacts in there, bimetallic strip, and just clean them up. Get some cleaning chemicals, and obviously with all the health and safety, try and clean them up if you can, and then fit everything together, as you should do it, and then put it back in. It's only going to be a temporary fix. Once they've gone to that extent, it's a problem. But it might be enough to hold you over for a couple of weeks or a month until you can order a spare part. So that's one way to look at it. You could have an iced up evaporator on the inside. Again, the energy cost goes quite high because it still tries to evaporate, to cool down, but if the cold air can't go anywhere because it's all iced up, you will find that a lot more energy is used up with your fridge. And maybe it's worthwhile to check at home as well if you've got a fridge which is where the evaporator, so the cold bit inside is hopelessly iced up, is maybe time to de-ice the thing. Take all the food out, spend a couple of hours, get rid of all the ice and then put it back in again. You will notice that it'll be a lot cheaper to run. And then the last one, which I mentioned to start off with, is electrical faults. Just check whether the fuses are okay, whether there's power getting to the refrigeration unit. Make sure that the wiring is okay. Make sure that there's power to the unit. Make sure that fuses inside the unit haven't blown. And then also make sure that you get power everywhere where you should get it. Obviously, it's got to be done by a certified electrician or somebody that's authorized to do it. But that's normally the checks you will be doing with this. Last one is for a refrigerator using a compressor. You always need electricity. For evaporative cooling, you can actually get away without electricity. You don't necessarily need electricity, but if you have some means of forcing air over the water, you would obviously enhance the effect of everything cooling down. So they're pretty much the two things. Just to sum it all up, we've been looking at two types of cooling. We've been looking at refrigerated cooling, we've been looking at refrigerants, we looked a little bit at maintenance, and then we've also been looking at evaporative cooling. Evaporative cooling, just an ancient method where water is just evaporating, and as a byproduct you get a cooling effect, and this cooling effect can be used within industry for a very cheap way of cooling things down. It is used already in power plants and things like that where they use evaporative cooling. And there are also air conditioning units which make use of evaporative cooling, which is especially suitable in dry climates, not to be advised to be used in wet and damp climates. Possibly the UK, evaporative cooling wouldn't be a good idea here for room climate control, because we do get a lot of hot days with a lot of rain, and if it gets really hot and muggy, you want some cold, dry air, and a traditional air conditioning unit with a compressor is ideal for these purposes. Okay, thank you very much for listening to this talk and to these units. And hopefully the next online sessions will go better, and obviously it's going to be a lot more interactive, so you don't just have to listen to a bloke talking without a break. And it's better for me as well, because I don't like talking without a break either. Anyway, thanks a lot for listening. I'll hopefully get everything sorted next week. I think I know what the problem was. I could pinpoint it down to a computer that's crashed, and it just never came back up again properly. So we should be okay. I'm going to have some backup systems next week, so if one crashes, I can go on the other one. Okay, talk to you soon. Bye-bye.